We're going to look at some more applications of the integral, and here we're going to find area in the plane, or areas in the plane, and this is a little different than what we've been doing. I mean, the integral itself, if you think about it, captures net area between the x-axis and the curve. But we can find areas between curves wherever those curves happen to be in the xy plane, and it's pretty intuitive how you would do it. This diagram here is supposed to kind of lead you to understand why it ends up being what it is, but essentially anytime you've got one function that's strictly bigger than or equal to another function on a certain interval, if you want the areas between them, technically you draw these rectangles, you get the approximate area, and then you let the number of rectangles go to infinity. But when you do all that out, you're essentially just going to be taking the areas or evaluating the integral on that interval of the difference between the two functions. So, I mean, maybe even the first thing I should have put here is it's the area under f of x minus the area under g of x. But by property of integrals, you could just write that like that. All right, so we'll use this idea to model some problems to get some areas in the plane. All right, so let's take a look at a few examples. In pretty much all these examples, I'm not actually going to get an answer out because really the point of this is to model the problem, not evaluate the integrals. So I don't want to waste too much time, evaluating integrals that you could either do with a calculator or using the fundamental theorem. But modeling the integrals that represent the area is important. So this says to find the area between y equals x squared minus x minus 6, which is pictured here, the x-axis, and between the vertical lines x equals 1 and x equals 4. So I'm going to put those vertical lines in. Now, the way this is worded, we're really not even finding the area between two curves necessarily. I guess the x-axis, you could call that a curve. But it's a good start just so we can get used to what we've been doing all along. The one thing we have to keep in mind is this word area means to count. It means count all area positive. So that's important because the integral itself gives net area, so it'll count some area as negative, so we'll have to adjust that integral to make sure that area gets counted as positive. So if we can sketch the area that's being described here, if it's trapped between the curve, the x-axis, and those two vertical lines, it's this area and this area that we need to find, that we need to evaluate. So let's start with the first section. So there's section A and there's section B. So section A, well, section A would be counted as negative, so we need to actually negate that area. So the way we do that is we just say, okay, well, the integral, this is the integral from 0 to 3 of x squared minus x minus 6. But that's going to give us a negative value. So I'm going to want to negate that. And now it's positive. And then I'm going to add that to the integral from 3 to 4, or area B, which is, again, it's under the same curve. All right, and there we have it. So this was a pretty basic, simple example, but just the style of this this problem is what you're going to see in the next few examples. But again, make sure you adjust to count all areas positive. The other thing you could do while I have this up, that's one acceptable answer. The other thing you could do is you could just say, look, I want this area to all be counted as positive. One way to make that happen is you can take the absolute value of this function, and when you take the absolute value of functions, it reflects all the negative y values to become positive y values. So, for instance, the graph of this, if you took the absolute value, let's call this, I'm going to do it in black, I think. So the absolute value of x squared minus x minus 6. Right, you'd have that piece. That's already positive, but the bottom part of that parabola is going to do this. I'm doing the best I can to reflect it. It's a little off. It shouldn't go quite so high there. But the point is, when you take the absolute value, now that area counts as positive. So what you could do is you could just integrate from 0 to 4, and to count all that area as positive, just do it under the curve, the absolute value of x squared minus x minus 6. That's a good thing to do if you know you have a calculator on you, and you can just plug this into the calculator. It's not useful if you have to do it out by hand, because the antiderivative of absolute values are not something we know, and you'd have to, I mean, to evaluate it, you'd end up having to break it up anyway, even if you wrote this down. But these are both correct ways of representing that area. Now let's move on to a different example where we're actually finding the area of between two curves, one of which is not an axis. So this says find the area of the region bounded above by y equals x plus 6 and below by y equals x squared on the interval 0 to 2. So the first thing we need to do is graph the two functions. So y equals x plus 6 is a line with a y-intercept of 6 and a slope of 1. And then y equals x squared has our familiar shape, our familiar parabolic shape. Alright, and so the area bounded above by y equals x plus 6 and below by y equals x squared, but on the interval 0 to 2 is describing this area here in black. Alright, so make sure you read that carefully. It says, again, bounded above by y equals x plus 6 means that's the upper boundary, and the lower boundary is y equals x squared. And so this integral is relatively easy to write down. You could think of it as you could break it up into two integrals. You could say, well, I'm going to do the integral from 0 to 2 of y equals x plus 6. Now that would get you all that black, but it would also get you some of this this purple in here, or all of this purple in here, right? Because it would be the area just under x plus 6. But you'd want to subtract the area under the parabola, so you would subtract. You would subtract the area under x squared, and now you've gotten rid of that purple. Now because the limits of integration are the same, you can just write it as one integral if you'd like, and that would be perfectly okay. All right. This problem is similar to the last one in that the same two curves are being considered. It's just that this is asking something more straightforward. It says find the area enclosed by y equals x plus 6 and y equals x squared. So that sort of implies that they're trapping area. If you graph these two guys, they're going to be trapping some area, and we just need to set up an integral that would actually evaluate that or represent that area. So we've already seen that y equals x plus 6 has this shape. And then y equals x squared looks like that. And so I can stop graphing because you can see now the area that they're describing is this area in blue here. So since x plus 6 is always the function on top, you can just represent this integral as the integral of x plus 6 minus x squared. The thing you have to consider is what the limits of integration are. Now it's easy to see here because I graphed it and I picked functions that made the intersections perfect integers. But let's just assume for a moment that you actually didn't see that clearly this is going from -2 to 3. You could figure that out by just solving this equation: x plus 6 equals x squared, right? Find the x values where those two curves are the same, or where they intersect. And then, of course, this turns into just an algebra problem of factoring and you get x equals -2 and 3. And so there's our final answer. So that one added nuance there was we had to go figure out where these two curves actually intersected. They didn't tell us to evaluate the integral on a specific interval.